Hello everyone. Hope you are doing very well. As you all know that today we are going to cover the theory part 8 of D and F block elements. So let's begin our today's topic, that is NCRT chapter 4 D and F block elements theory part 8, and the section we are going to cover is 4.7. Along with that, some exercise question 4.1, 4.7, 4.15 and 4.31. This is disclaimer. So let's talk about the objective of today's lecture. So after attending this lecture, you will be able to describe the properties of F block elements and give a comparative account of lanthanoids and actinoids with respect to their electronic configurations, oxidation states, and chemical behavior. The topics that we are going to cover today according to the NCRT, they are: the first is section 4.7, some applications of D and F block elements, and then we will continue to practice some exercise questions from our NCRT textbook, which is marked as 4.1, 4.7, 4.15 and 4.31. So let's begin with our first topic, that is 4.7, some applications of D and F block elements. So the importance of D block elements in the materials and industry. So industrially, how the D block elements is important. First of all, iron and steel. So the most important construction materials they are, that is iron and steel. Industrially and in the construction process, they used widely the iron and the steel. So they are the most important, considered as the most important construction materials. Production involves, their production, the iron and steel production involves the reduction of iron oxides. If we have iron oxides, you have to reduce them to get the iron from that. Okay, so production of iron involves the reduction of iron oxides, removal of impurities. Secondly, you have to remove any impurity if present in the produced iron, so that it can be used beneficially or properly in the industrial purposes, okay, for the construction material and for different uses. Then the addition of carbon and alloying metals. Then you have to add carbon and other alloying metals like chromium, manganese and nickel. Special purpose compounds. So there are some special purpose compounds, that means some compounds that we used for some special purpose. First is titanium oxide. This is used in the pigment industry. The another is manganese oxide. This compound is used in dry battery cells. Okay, dry battery cells is a type of cell which is used widely, and in this construction of dry battery cells, this compound MnO2 is used. So there are some compounds that are used for some special purposes. Next, importance of D block elements in the materials and industry. Continuing on this, next importance of the D block elements are battery industry requirements. So basically the industry in which the battery is made up of. Okay, so like battery industry, in the battery industry, D block elements have their own requirements. The first one is zinc. In battery, we use zinc. We also use nickel and cadmium in the battery industry. The next importance of D block elements covers the topic coinage metals, which covers group 11 elements from the periodic table. So, what are coinage metals? They are basically the group of, you can say, metallic elements which is historically used to mint the coins. For example, copper, silver, gold, right? So, they still called coinage metals. From that, silver and gold are restricted to the collection items. Okay, so gold and silver are restricted to collection item, means the items that are collected uh, from various places, you can say, or for various purposes. So that the items that are stored or that are collected, that are generally made up of the silver and the gold. Contemporary UK copper coins, the other one coinage metal is copper. So the contemporary UK copper coins, like of 1 pence or 2 pence, they are copper coated steel. Okay, so those copper coins which are contemporary UK copper coins, like 1 pence, have a value of 1 pence and 2 pence. They are copper coated steel. They are made up of a copper coated with the steel element or surface. Silver UK coins, meanwhile, the silver UK coins, which having the value of 5, 10, 20 pence, they are a copper and nickel alloy. So they are, the silver UK coins are made up of the copper and nickel alloy. Catalytic applications of D block metals and their compounds. Now we have seen that the D block metals have their own catalytic applications and catalytic uses, right? So what are those, and what are the D block metals and their compounds that is being used as a catalyst? So essential catalyst in the chemical industry. In the chemical industry, we use D block metals and their compounds as the an essential catalyst. Some of them are V2O5, vanadium oxide, catalyzes the oxidation of SO2 in the manufacture of sulfuric acid. Now, where we use this vanadium oxide, a D block compound, metal compound, in the catalyzation of oxidation of sulfur dioxide while the preparation or manufacture of sulfuric acid H2SO4. So in this process, we use this vanadium oxide as a catalyst to increase the rate of reaction. TiCl4 with aluminium CH3 whole thrice. Okay, so we use this as a catalyst and it forms the basis of Ziegler catalyst, which is used to manufacture the polythene or polyethylene. Okay, so the Ziegler catalyst, which we use while the manufacturing of polythene or polyethylene, Ziegler catalyst basis has been formed using this TiCl4 with aluminium CH3 whole thrice, which is a D block metal compound. Titanium is a D block metal. Iron catalyst. Iron is also an element from the D block. So, iron catalyst is used in the Haber process for the production of ammonia from N2 or and H2 mixture. So the Haber process is a name process which is for the ammonia preparation or production from N2 and H2 mixture. And in this process of Haber, catalyst uses of iron. Okay, iron we use as a catalyst to increase the speed of the reaction to get the more production of ammonia. Next is nickel catalyst. Nickel is also a D block metal and it is used as a catalyst which enables the hydrogenation of fats. So while the hydrogenation of fats, that means conversion of fats or you can say hydrogenation or of fats to the simple alkenes, we use nickel as a catalyst to enable that process. Next is PdCl2, palladium dichloride. This catalyzes the oxidation of ethine to ethanol in the Waker process. This is a name process, Waker process, where a alkyne is converted to you can say aldehyde, right? Alkyne to aldehyde. So oxidation of triple bonded alkyne, ethyl, ethine to ethanol and aldehyde. Okay, and this oxidation process is catalyzed by PdCl2, where this PdCl2 is a D block metal compound. Next, nickel complexes. They are useful in the polymerization of alkynes and other organic compounds such as benzene. So when you are talking about the polymerization, that means adding of many smaller molecules together to get a bigger or a longer chain compound of either alkynes and other organic compounds such as benzene. We use nickel complexes as a catalyst to increase the rate of this polymerization reaction. So these are the catalytic applications of D block metals and their compounds in various processes chemically in the chemical industry. Other important applications of the D block elements are: first is the compound silver bromide, which is relied upon the photographic industry. Why? Due to its special light sensitive property. So other than the catalytic applications, the other application of D block element is like, if you observe in the compound silver bromide, it is used in the photographic industry due to the presence of special light sensitive property in this compound silver bromide. Okay. Now let's see the mnemonic of 3D series. So you remember we have studied about the 3D series in the very first of the DNA block elements theory, right? So how you can learn the 3D series element by element in the successive manner. So let's see the mnemonic of 3D series for that. Sachin Tendulkar, very crazy man, फिर कोई नया cup जीतेगा. Or you can say Sachin Tendulkar, very crazy man, then anyone new cup will win. Okay, how you can arrange that or how you can relate that with the elements of the 3D series? Sachin is basically representing scandium. Tendulkar is representing titanium. We are just, this is mnemonic of 3D series, basically a easier way to learn the elements present in the 3D series in the successive manner. So we just have to relate some word with the symbol or the element name to learn that yes, this element is coming in the third place or the fourth place in this series. Okay, so like Sachin we are referring to as scandium, so that means first element. Tendulkar we are referring to titanium because Ti is present, so Tendulkar, titanium. Okay. Next is very, we are relating with vanadium, that is V. Crazy, we are relating with Cr, that is the symbol for chromium. Man is we are relating for manganese, symbol Mn. Fir, which is we are relating with ferrum, that is iron, Fe. Koi we are relating with cobalt, that is Co. Naya we are relating with nickel, that is Ni. Cup we are relating with cuprum or copper, that is Cu. And lastly jeetega, that is we are relating with zinc, that is Zn. Okay, so we are relating our mnemonic word with the symbol or either the element name, whether which which is very relative to the Hindi word, whether it is symbol or it is the element name. So by that you can easily learn the 3D series, that Sachin Tendulkar, very crazy man, फिर कोई नया cup जीतेगा. Okay, so this is how you can learn the mnemonic of 3D series. So this is the mnemonic of 3D series. You can learn it or you can write it somewhere. Okay, and this will be very helpful while reminding the order. If in some question the order you is asking, the question is asking about the order of either atomic radii, ionic radii, ionization enthalpy, electronic configurations, right? That you can easily get or remember by remembering this mnemonic of the 3D series. Similarly, let's see the mnemonic of 4D series, the next series coming after the 3D series. So it is having this line, यारी जरा निभा मौत तक, रुकावट राह में पड़े अगर कोई. Friendship a little, fulfill death till obstacle path in fall, if any. So how can you relate that? The yari, you can relate it with deuterium, that is Y. Zara, zirconium, that is ZR. Nibha, that means niobium, that is NB. Okay, Nibha you can more relate with the symbol NB. Moth is related to the symbol MO, molybdenum. Tak is related to the symbol TC, technetium. Then Rukavat is for ruthenium, that is Ru. Raha is for rhodium, that is Rh. Pade, that means palladium, that means Pd. Agar, that means argentum or silver, that means Ag. Koi, that means cadmium, Cd. Okay, so this is how you can learn the pattern, or you can learn the elements coming in the 4D series successively after remembering this mnemonic of 4D series. Okay, so यारी जरा निभा मौत तक, रुकावट रहा पड़े अगर कोई. Deuterium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, argentum or silver, and cadmium. Now let's see the mnemonic of 5D series, the next series after the 3D and the 4D series. So for the 5D series, we have this la hafta ta varna re udhar idhar pitai aur hogi. La hafta ta varna re udhar idhar pitai aur hogi. Right? So this is the mnemonic for 5D series. How you relate it? La for lanthanum, that is La. Hafta for hafnium, that is HF. Ta for tantalum, that is Ta. Varna is for wolfram or tungsten, more related to that symbol W. Then Re is for rhenium, that is Re. Then Udhar is for osmium, Os. Then Idhar is for iridium, that is Ir. Pitai is for platinum, that is Pt. Or is for gold, that is Au. And Hogi is for Hg, that is mercury. Okay, so this is how you can learn the 5D series element by element successively, and this is an easy way of remembering it. Like, and it will going to help you in many way in getting the correct order of anything, like atomic radii, ionic radii, ionization enthalpy, or electronic configuration. If you want to check how many electrons will be there in the outermost orbital, that is also going to help you through this mnemonic of 5D series, right? So you can learn it. Next, let's see the mnemonic of our next series, that is 6D series, which comes after 5D series. So it has this, actually रमन डॉक्टर से बोले हंसकर मत डरो रहेगा काम. Okay, so actually रमन डॉक्टर से बोले हंसकर मत डरो रहेगा काम. Okay, so if you see, actually is relative with actinium, that is AC. Raman is for rutherfordium, that is Rf. Doctor is for dubnium, that is Db. Se is for seaborgium, that is Sg. Bole is for borium, that is Bh. Husker is for Hassium, that is HS. Mat, that is Metanerium, that is MT. And Duro is for Darmstadtium, that is DS. Rahega is for Rongenium, that is RG. Calm is for Copernicium, that is CN. Okay, so this is the 60 series and the mnemonic of 60 series, which you can learn, and it is going to help you in many way later. Okay, so actinium, actually रमन डॉक्टर से बोले हंसकर मत डरो रहेगा काम. Actinium, rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, darmstadtium, rongenetium, copernicium. Okay, so this is the 60 series. Now the mnemonic of lanthanoid series. After the 3D, 4D, 5D and 6D, we have learned about the lanthanoid series, right? So lanthanoid series elements and its mnemonic. This is the table showing the mnemonic of lanthanoid series, their element symbol and the element name with the mnemonic word. So element name is cerium, symbol CE, mnemonic word is sir. Then element name praseodymium, praseodymium. The element symbol is PR and the mnemonic word is per. So if we first read this mnemonic word, सर पर नदी पैरों में समुंदर, अरे गॉड तुम दयालु हो और तुम यहाँ भी लूटोगे. ओके, सो सर पर नदी पैरों में समुंदर, अरे गॉड तुम दयालु हो और तुम यहाँ भी लूटोगे. So how it is related? Sir is related with cerium, per is related with praseodymium, nadi is related with neodymium, Parome is related with promethium, samundar with the samarium, array is for europium, the symbol is EU, god is for gadolinium for GD, tum is for terbium, that is TB, dayalu is for dysprosium, that is DY, ho for holmium, that is HO, or for erbium, that is ER, tum for thulium, that is TM, यहाँ भी for ytterbium, that is YB, and lutoge is for lutetium, that is LU. So this is the mnemonic of lanthanoid series. You can learn it and it will going to help you to identify the element series. Now after the lanthanoid series, we have talked about actinoid. So let's see the mnemonic of actinoid series. Actinoid series elements and its mnemonic. एक था पागल उल्लू, नेपाली उसके पुराने आम कम बिके, उसने कॉफी ऐसी फरमाई मैडम नूडल लाई. Okay, so you can see this in table that we have given element name of actinoid series, their symbol and their mnemonic word in Hindi and English both. So it is था पगलू उल्लू, था पागल उल्लू, नेपाली उसके पुराने आम कम बिके, उसने कॉफी ऐसी फरमाई मैडम नूडल लाई. Okay, so Tha is for thorium, that is TH, Pagal for protactinium, that is PA, Ullu for uranium and U, Nepali uske is for neptunium, NP, Purane is for plutonium, that is PU, Am is for americium, that is AM, Kam is for curium, that is CM, Bike usne is for berkelium, that is BK, and coffee is for californium, CF. Coffee is more related to the CF symbol. SE is for Einsteinium, that is ES. Fermi is for fermium, that is FM. Similarly, Fermi is more related to the symbol. Madam is for mendelevium, that is MD. And noodle is for nobelium, that is NO. And Li is for laurentium, that is LR. Where Li is more related to the element name. Okay, so this is how you can learn the series of actinoid by using the mnemonic word. Okay, let's practice exercise question which is marked as 4.1. The question is, write down the electronic configuration of. So we have given some parts of this question and you have to write down the electronic configuration of each part of each ion. First is chromium 3 positive, then PM 3 positive, right? Then your copper positive, then cerium, CE is cerium 4 positive, then cobalt 2 positive, then lutetium 2 positive, and then manganese 2 positive, and then TH is for thorium, right? So thorium 4 positive. You have to tell the electronic configuration of each ion from first to the eighth part. So you can do this right? Because you just have to remember here the general electronic configurations of the D block or F block if the element is from D or F respectively, and then you can fill out the electrons as per the atomic number, and then you can release the electrons as all the ions are having positive charge. So the required number of electron you have to remove from that configuration, then you can get the final configuration for the ions. So you got some time, try to solve this, and then we will see the correct answer. Okay, let's see. So for this question, let's see the first part for chromium 3 positive. So neutral chromium has atomic number of 24. So the electronic configuration of chromium will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. So we just filled the 24 electrons in different orbitals as per the rules of filling of orbitals. And to find the chromium 3 positive configuration, we have to remove 3 electrons, right? Having 3 positive charge means the 3 number of electrons is donated by or loosed by the chromium. So when you remove 3 electrons, it will be removed from first 4s orbital and then from 3d subshell. So chromium 3 positive configuration will become 1s2, 2s2, 2p6, 3s2, 3p6. From 3d you have removed 2 electrons, so it will be 3d 3. After removing 2 electrons from 5, we obtain 3 electrons here, and 1 electron is already removed from 4s. So 4s will not be here. So chromium 3 positive electronic configuration will be this. Or you can also write it as argon 18 3d3. That means argon is a noble gas. So it is chromium 3 positive is attaining noble gas configuration of argon after filling of 18 electrons, and only 3d3, that is 3 electron of outermost orbital is going to be extra. So you can write this configuration of chromium 3 positive as argon 18 3d3. Now for the second part, for the PM is basically, let me see. Okay, PM is promethium. Okay, so for promethium, the neutral promethium is having an atomic number of 61. So electronic configuration of promethium will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2, 4d10, 5p6, 4f5, 6s2. So this is how you have to arrange the 61 number of electrons in different subshells for the promethium. Now you have to get the electronic configuration of promethium 3 positive. 3 positive charge means 3 electrons is going to be removed from its outermost shell. So promethium 3 positive will be 3 electrons removal. So 3 electrons, 2 from 6s2 and 1 from 4f5. So promethium 3 plus electronic configuration will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2, 4d10, 5p6 and 4f4. Okay, because 2 is released from the 6s2 and 1 is released from 4f5. So the remaining will be 4f4. Or you can also write it as xenon 54 4f4. Okay, so xenon is again a noble gas. So promethium 3 positive is attaining a noble gas configuration up to 54 electrons, and after that the remaining will be 4f4, which you can write it like that. So this is also the way you can write the electronic configuration of promethium 3 positive. Okay. Now for the third part, for the copper, the neutral copper has atomic number of 29. So electronic configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Now for copper positive, one positive charge means only one electron is removed. That is also from 4s subshell, because this 3d10 is going to be stable one, right? So if only one electron we have to remove, so it will be removed from this 4s1. The configuration of copper positive will become then 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Or you can also write it as argon 18, 3d10. Okay, argon is a noble gas. So argon configuration up to the 18 electrons and then 3d10. Now for the fourth part, that is for cerium, the neutral cerium has atomic number of 58. So configuration or electronic configuration of cerium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2, 4d10, 5p6, 4f1, 5d1, 6s2. Okay. Now the cerium 4 positive means 4 positive charge, it has to lose 4 electrons from it. So we have to remove 4 electrons. So cerium 4 positive will become 2 electrons will remove from here. 1 is removed from 5d1 and 1 is removed from 4f1. The remaining configuration will be for cerium 4 positive, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2, 4d10, 5p6. Okay, so up to 5p6 we have this configuration for cerium 4 positive. The left or the another outermost orbital electrons, that is 4, will be removed. Or you can also write cerium 4 positive configuration as the xenon 54 configuration. Okay, so cerium 4 positive configuration is similar to the xenon noble gas configuration, so you can write it also like that. Now the next part, that is for fifth part, for cobalt, the neutral cobalt has atomic number of 27. So the electronic configuration of cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Or you can also write it as argon 18, 3d7. Argon is a noble gas. So argon 18, 3d7. Now let's see for the sixth part, that is for neutral lutetium. So neutral lutetium has an atomic number of 71. We have to find out the configuration for lutetium 2 positive. So if neutral lutetium is having atomic number 71, the electronic configuration of lutetium will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2, 4d10, 5p6, 4f14, 5d1, 6s2. For the lutetium 2 positive, we will remove 2 electrons from the 6s subshell, right? So lutetium 2 positive will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 4f14 and 5d1. So the outermost orbital having 2 electrons in the 6 subshell is going to be removed, and the lutetium 2 positive configuration will be this. You can also write it as xenon 54, 4f14, 5d1. So these are the configurations for lutetium 2 positive. Then For the seventh part, that is manganese 2 positive, the neutral manganese has atomic number of 25. So the configuration of manganese is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. This is the configuration for manganese having atomic number of 25. So for the manganese 2 positive, we have to remove 2 electrons from the 4s subshell, right? Because 3d5 is the stable one. So we have to remove the outermost orbital or outermost subshell electrons, that is from the 4s. So Mn2 positive will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. 2 electrons will be removed from 4s subshell. Or you can write the configuration of Mn2 positive as argon 18, 3d5. Now, let's see the 8th and the last part of this question, that is for thorium 4 positive. The neutral thorium has atomic number of 90. So the configuration of thorium is radon 86, 6d2, 7s2. This is going to be we can write the configuration in the form of noble gas configuration, right? So up to 86, we have a noble gas atomic number for the radon. So we write the radon 86 and the left electrons as 6s2, 7s2 after filling them in the 6d and 7s subshell. Okay. Now for the thorium 4 positive, we have to remove 4 electrons, right? So the thorium 4 positive configuration will become of the radon configuration of 86 atomic number, because 4 electrons will be removed, 2 from 7s and 2 from 6d. And this will be the final electronic configuration you will get for thorium 4 positive. Okay, let's solve another exercise question, that is 4.7. What is lanthanoid contraction and what are the consequences of lanthanoid contraction? So you have to tell about the lanthanoid contraction in this question. Remember, when we studied about the lanthanoid series, then we have talked about this. So you have to answer this question on that concept basis. So you got this, you got some time, try to solve this and then we will see the answer. Okay, let's see. So the lanthanoid contraction, let's see the definition of it. To define, the lanthanoid contraction refers to gradual decrease in ionic radii of lanthanide series elements from lanthanum to lutetium as we move from left to right across the lanthanoid series. Okay, so when we move across the lanthanoid series from lanthanum to lutetium, there is there is observation of a gradual decrease in the ionic radii of the elements, that is referred to as lanthanoid contraction. And this contraction is occur why? Due to the ineffective shielding or poor shielding of nuclear charge by the f electrons. Let's explain the shielding effect. If you want to understand the shielding effect in the context of electronic configuration, shielding effect describes that how the inner electrons in an atom, how the inner electrons can shield the outer electrons from the full effect of nucleus positive charge. So as the size will increase, the nuclear positive charge will increase, which is going to be like the outer electrons is going to be protective towards the inner electrons is going to be protective towards the outer electrons. So inner electrons shield the outer electrons from this nuclear positive charge, and this is refers to the shielding effect. Okay. Now in case of lanthanoids, f orbitals where the f electrons are available, f orbitals provide poor shielding compared to the s and the p orbital. In the case of lanthanoids, the f orbitals where the f electrons are available, they reside. The f orbital provide poor shielding compared to the s and the p orbital. Okay, so comparing to s and p orbital, the f orbital provide the poor shielding to the uh, electrons, and due to which they will form they will going to be more attractive towards the nucleus positive charge, right? This means that as more f electrons are added, the outer electrons experience a stronger effective nuclear charge, right? So because of the poor shielding of f orbital, when you add upon more of electrons in the f orbital, the f electrons are going to experience a stronger effective nuclear charge, due to which the size is going to be decreased with the addition of each electron. Now, what are the consequences of lengthenoid contraction? So, decrease in the ionic size, the first consequence, that as the nuclear charge or effective nuclear charge increases, and poor shielding is already present for for the f orbital. So, as the nuclear charge is increasing due to the poor shielding, size of lengthenide ion going to be decreased, because the outermost electron and the coming electron are going to experience the strong nuclear charge, due to which the ionic size, the lengthenoid ion size, is going to decrease. Increase in the ionization energy. So the stronger attraction between the nucleus and the outer electrons. So the outer electrons are more strongly held by the nucleus due to this poor shielding. So the strong attraction buildup between the nucleus and outer electrons, which will result in the higher ionization energy, which will make it more difficult to remove the electron from the outer orbital, from the lengthenoid elements, right? So there is also the increase in ionization energy due to the lengthenoid contraction. Ionization energy means the energy you have to provide to remove the electrons from the element. But if the nucleus and the outer electrons are strongly held together due to the poor shielding provided by f orbital, it will result in the higher ionization energy that you have to provide to remove an electron. Another consequence is that similar chemical properties. Now, the decrease in the size and increase in the ionization enthalpy lead to similarities in chemical properties among the lanthanoids, which make it challenge to separate them from one another, because they start to behave like same. They start to show the similarity in their chemical property. So if you want to separate them from each other, it is going to be more difficult. And the last consequence of the lanthanoid contraction is impact on coordination chemistry. So the contraction of the sizes, the gradual decrease in the size, affect the coordination number and geometry of lanthanoid complexes. Okay, so coordination number is basically the amount of the ligands that are going to be connected with the central metal, which is generally the DNF block element. Okay, so this contraction will going to affect the coordination number of the complex and the geometry of lanthanoid complex, which is going to influence their chemical behavior and the reactivity. Okay, because bonding is effective, the geometry is affecting, so the chemical behavior and the reactivity will going to be effect for the coordination chemistry of lanthanoid complexes. So these are the consequences of lanthanoid contraction occur in the lanthanoid series elements. Okay, let's solve the another exercise question, which is 4.15. Describe the oxidizing action of potassium diachromate and write the ionic equations for its reaction with iodide, iron plus 2 solution, and hydrogen sulfide, H2S. So you have to tell the oxidizing action of potassium dichromate, that how the potassium dichromate oxidized, and the ionic equation when the potassium dichromate react with these three atoms, that is iodide, iron plus 2 solution, and H2S. So you have given some time, try to solve this, then we will see the correct answer. Okay, let's see. So, first of all, potassium diachromate, which is a strong or which act as a strong oxidizing agent. Okay, it is used as a primary standard in the volumetric analysis. Okay, volumetric analysis means it is used to determine the amount of substance by measuring the volume of solution needed for complete chemical reaction. Okay, so in that process we use the potassium dichromate as a primary standard. Oxidation action of the dichromate ion in an acidic medium can be represented as follows. So in the acidic medium where H positive protons are present, how the dichromate ion will going to show its oxidizing action? So Cr2O7 2 minus plus 14 protons plus 6 electrons, and you are going to get 2 chromium 3 plus 7H2. So you are going to convert the diachromate to the chromate ions, Cr3 positive. Okay, like chromium ions in the 3 positive charge. The E naught for this is 1 positive 1.33 volt. Okay, the iodide ion, that is I negative, is oxidized to I2 by the acidified solution of the potassium diachromate. Potassium diachromate acidified solution can oxidize the iodide ions to iodine molecule. The reaction follows. Dichromate ion reacts with the protons and the iodide ions in the acidified solution and converts it to the chromium ion, 7 molecules of water and 3 molecules of iodine. So iodide to iodine it is converting or oxidizing. Right? So these are the processes showing the oxidation action of dichromate ion. First of all in the acidic medium, and then by the oxidation of the I negative to the iodine molecule. Now, for the potassium dichromate act as a strong oxidizing agent, okay, in the second part, iron plus 2 solution. So, it is used as a primary standard in the volumetric analysis. This we have know. The oxidation action of diachromate ion in an acidic medium can be represented as follows. So diachromate reacts with protons and 6 electrons, give us chromium ion and 7 molecules of H2O. The E naught will be 1.33 volt. Now, when the ferrous salts, that is Fe2 plus, are treated with the acidified potassium dichromate, they are oxidized to the ferric salt, that is Fe3 plus salt. Okay, so the dichromate is going to oxidize the Fe2 plus to Fe3 plus. So the reaction is that diachromate reacts with the, or you can say acidified diachromate reacts with this ferrous salt Fe2 plus, and we will get chromium ion plus 7 molecules of water and the ferric salt Fe3 plus. So Fe2 plus to Fe3 plus. Now for the third part, that is the H2S, hydrogen disulfide, or you can say hydrogen sulfide. Okay, so for this third part, we know that potassium dichromate will act as strong oxidizing agent, right? Strong oxidizing agent means it is going to oxidize the others and get reduced itself. It is used as a primary standard in the volumetric analysis. The oxidation action of dichromate ion in an acidic medium can be represented as follows. So, how the dichromate ion show is its oxidation action or its oxidation process in acidic medium. So dichromate ion reacts with proton, gains some electron and converts to chromium 3 plus and produce 7 molecules of water. The E naught for this process is positive, that is a positive 1.33 volt. Now hydrogen sulfide is oxidized to sulfur by the use of diachromate. So diachromate when reacts with the protons and the hydrogen sulfide, it is going to oxidize the hydrogen sulfide and produce sulfur atoms, along with that 7 molecules of water and chromium ions. So this is the process happening while the oxidation process or oxidation action of potassium dichromate showing in the case of H2S. And the ionic equation will be this. So we have seen for all the three parts the oxidizing action of potassium dichromate and their ionic equations respectively. Right? Okay. Let's see the another question, that is exercise question 4.31. It says that use the Hund's rule to derive the electronic configuration of cerium 3 positive ion and calculate its magnetic moment on the basis of spin only formula. So you have to do two things. First of all, you have to use the Hund's rule for deriving or for writing the electronic configuration of cerium 3 positive ion. Then you have to calculate the magnetic moment of cerium 3 positive ion on the basis of spin only formula. So you have provided some time. Try to solve this. Then we will see the correct answer. Okay, let's see. So for this question, so we have to write the cerium electronic configuration first using the Hund's rule. It will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 4f1, 5d1 and 6s2. Okay. Now, like for the magnetic moment, it can be calculated as mu is equals to under root n plus 2. Right? So, where the n is representing the number of unpaired electrons, right? So we have seen the cerium electronic configuration, which is given by this, and we have seen the magnetic moment spin only formula, which is this, that is mu equals to under root n plus 2. N is representing the number of unpaired electrons. Now you have to identify the cerium 3 positive ion configuration. So you use the cerium configuration to determine the electronic configuration of cerium 3 positive by just losing or removing its 3 outermost electrons, right? So electronic configuration of cerium 3 positive will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6 and 4f1. Now, for this cerium 3 positive ion, the n you have to predict, that is the number of unpaired electron in the outermost shell, it is 1, right? 4f1. So 5p6 is fulfilled because in the p subshell we can fill at most 6 number of electrons, so it is fulfilled. And before it also every subshell is fulfilled, only the unpaired electron is going to be present in the 4f subshell, which is going to be 1. So n value is 1, n is representing the unpaired electron. So the magnetic moment therefore will be under root n plus 2 Bohr magneton. We put the n as equals to 1, so mu will be 1 times 1 plus 2. 1 plus 2 is 3, 3 times 1 is 1. So mu will be under root 3 Bohr magneton, or mu will be 1.73 Bohr magneton after calculating the under root 3 value. I can tell you one trick here, that you know that under root 4 will be 2, right? 2 times 2 is 4, under root 4 will be 2. So under root 3 is very close to under root 4, right? Under root 4 is 2. So under root 3 will be lesser than the value of under root 4. That means lesser than the 2. So it will be relating to 1 point something. Okay, 1 point greater than like 6 or 7. Okay. So the under root 3 value will be 1.73 Bohr magneton. This is how you can calculate the magnetic moment using the spin only magnetic formula for the cerium 3 positive ion, and this is the electronic configuration for cerium 3 positive ion, which we have written by using the Hund's rule, which we use for writing the electronic configuration of any atom or element. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.